All right, well, good morning, everybody. So as we begin today, first just a reminder that the homework put on the board last week is due on Wednesday, so please don't forget to bring that with you next time. By the way, it doesn't have to be on engineering paper, whatever paper works good for you. These days, to be environmentally conscious, you could even use recycled paper. Just don't write on the side that has other writing on it, but otherwise, any kind of paper is fine for turning in the homework. Here's the new homework assignment for the week. So this is for the entire week. These will be due next Wednesday. And the ones with an asterisk, I just want to note that I do want you to solve them using variable-specific heats, regardless of what the problem statement says. The ones with the asterisk, please, variable-specific heats. And we did talk about that a little bit last time. Certainly we'll talk about that more as we get into the new material this week. Nonetheless, and then lastly, just a reminder that you all have to show me proof of prerequisites. Everybody who took me last quarter, I already marked you off. The rest of you, many of you have already shown me. There's only about 10 people or so left who need to show me that proof. So just don't forget, please bring up proof that you've made at least a C- grade or better in ME 301. Also, let me just note that there's actually one spot left in this class. The waiting list has been cleared now, and we're down to 44. So if anybody is still trying to add, first come, first serve on Bronco Direct, I suppose, and today's the last day to add. So please make sure you take care of that right away. Some of you may know somebody who is trying to get into a thermal class this quarter. Send them a text. Let them know. Again, whoever signs up first will get that spot. So with that, let us just move on and continue talking about some review. Please note that most of what I went over last week was just review, right? And today it's going to be mostly new material, but just a couple last things to finish with regarding review, and this deals with cycles. We are going to be looking at cycles, for at least the first month or so of this class, so some sort of a review of thermodynamic cycles is important. Let's note, please, that there's two cycles that we've talked about previously, one being the heat engine cycle and the other being the refrigeration cycle. We'll talk about the refrigeration cycle shortly. We'll start with the heat engine. Just keep in mind that if we have a heat engine, we're going to be adding some heat at high temperature, and the purpose is then to produce a certain amount of net work output. Now, we know that from the second law of thermodynamics, we can't do this all by itself, right? To turn heat into work requires rejection of heat simultaneously, so we also have to show our low temperature heat rejection at this point. Keep in mind that H stands for high or high temperature. This QH represents the input of heat, and L represents low or low temperature, and QL represents the heat that's rejected, or the heat output, if you will, from the cycle. Note that the net work output is going to be the difference between whatever work is produced by the cycle less whatever work is required by the cycle. So with this all in mind, it's the thermodynamic efficiency that we use as our performance parameter of interest. Certainly the higher the efficiency, the better the heat engine, right? The higher the efficiency means that we get more work per unit of heat input, or perhaps we could think of it as requiring less heat input for each unit of work. And that's really what we want, right? We're trying to maximize this. So this is just the net work output divided by the heat input. Now, please note that this can be written in any of our three different forms, right? We can write this on a per unit mass basis. These are all capital letters over here. On a per unit mass basis, we'd have lowercase work net output divided by the heat input, lowercase qh. So, whereas these terms are all either kilojoules or BTUs, these are kilojoules per kilogram or BTUs per pound. We could also take the time derivative. That should be an equal sign. We could also take the time derivative and note that the efficiency is also just the rate of net work output. We call that power, right? Divided by the rate of heat input. And we use the dot notation. Of course, the dot represents the first time derivative, or, if you will, per unit time data. Now, let's also understand that over a cycle, the total amount of heat transfer is also going to equal the total amount of work. I mean, this applies to any cycle. If this wasn't true, then it wouldn't be a cycle. I mean, keep in mind that as you go through the cycle, you have to begin and end at the same thermodynamic state, and the only way for that to happen is if the net heat output equals the net work production. So this certainly applies to all cases. We'll note in this particular case, if we're interested in the thermodynamic efficiency, then the net work output, which really represents the right-hand side, would simply have to be equal to the difference between the heat input and the heat output, which would represent the left-hand side. So using the dot notation here, in other words, the final version of this efficiency equation up at top, the net work is just the difference between Q dot H and Q dot L, and then divide it by Q dot H. And now this term could certainly be modified. We can just write it as 1 minus Q dot L over Q dot H. We could have actually gone through exactly the same thing on a per unit mass basis or on a total basis. We could also show that this is just 1 minus lowercase ql over lowercase qh. Okay. Lastly, let's also note that the net power output, again, is the difference between two terms, right? There's going to be some work output that is associated with this cycle. So this will be W dot out. And then minus whatever the work input, again, on a per unit time basis, we'd say the net power output, the power output minus the power input. And this is therefore just the net power output. By the way, I could put out here, and let's neaten that W up. Okay. So this is just something we should keep in mind. And when we start looking at actual cycles, we'll see that there's specific portions in the cycle or specific devices within the cycle that are producing the work output versus the work input. So of course we're going to get into this in more detail as we get into real cycles. For instance, if this were a cycle based on single stream steady flow analysis, for instance, if this were a gas turbine cycle like you should have covered in your 301 class, there would be a certain amount of work output from the gas turbine, but there would be a certain amount of work input from the compressor. So it's the difference between the two, work out minus work in, that's going to give you the net output, and that's what has to be used in the efficiency equation. All right, so what about a refrigeration cycle? What would that look like? And what would be the equations of interest? So refrigeration cycle now. So it's still a cycle. We could still show this just as a box with a circle in it. But a refrigeration cycle is different, right? The purpose of a refrigeration cycle is to take heat out of something that is cold and transfer it into something that's hot. That doesn't happen in the real world all by itself, right? In nature, heat is transferred from the hot thing to the cold thing, not the other way around. So when we operate a refrigeration cycle, we're actually taking heat input from a low temperature source, and then we're able to reject heat output into a high temperature sink. Okay? So in other words, we're taking heat out of the food that we're trying to keep cold in the refrigerator, right? And we're dumping that heat into the kitchen. We generally don't care how much heat is transferred into the kitchen. We feel it, right? We step up in front of the refrigerator, we feel the warm air blowing across our toes. That's the warm heat output from a refrigeration cycle. We could have also used an air conditioner to make the same statements. Nonetheless, this is a typical refrigeration cycle, but again, the second law of thermodynamics doesn't allow us to simply transfer heat from something cool to something hot, right? In order for this to work, we have to have some sort of work input. So we need to show the work input here as well, and that's going to be part of obviously the refrigeration cycle. Now, for a refrigeration cycle, we don't use the thermal efficiency anymore, right? Thermal efficiency, or what we might also just call thermodynamic efficiency, only applies to heat engines. For a refrigeration cycle, our performance parameter is called the coefficient of performance, just COP. And the coefficient of performance is simply the desired heat transfer divided by the required work. So the desired heat transfer divided by the required work. And of course, this is work input. Okay, so this is our coefficient of performance. Now, I will note that there are different desired heat transfers depending upon the nature of the refrigeration cycle. In fact, there's two broad categories of refrigeration cycles. The first would apply to things like a refrigerator or a freezer or an air conditioner. In this situation, the desired heat transfer, the numerator, is the amount of heat that we're able to pull out of the space that we're trying to keep cold, right? I mean, that's all we really care about in our fridge and our air conditioner, is just keeping cold, right? We don't really care how much heat gets rejected out into the environment. We're concerned with how much heat we can pull out of what we're trying to keep cold. So in this particular case, we use a subscript R. Nominally, that's for refrigerator, but again, it still applies to freezers, air conditioners, ice makers, that kind of stuff, chillers used on big buildings. So coefficient of performance is going to be the desired heat transfer, which of course is going to be the heat input from the low temperature source, right? So this is just going to be Q dot L, and then divided by the network. Okay, now I'm writing this on a per unit time basis. It doesn't have to be that way, of course. We could write it on a per unit mass basis. We can write QL over lowercase work net. It really just depends on the problem at hand and what kind of data we have. But certainly, this is the equation we would utilize for a refrigerator, freezer, or air conditioner. Now, this can certainly be manipulated. I'm not going to go through the proof. This was done in your earlier thermodynamics classes. But this can also be shown to equal 1 over, and then here we'd have Q dot H over Q dot L minus 1. So this is just an alternate form, or again on a per unit mass basis. We could just show it as 1 over lowercase QH over QL minus 1. So this is the performance parameter of interest. Now, again, we're trying to have this number as large as possible, right? What we're trying to do is maximize our benefit, which is the amount of heat transfer from the cold space, and we're trying to minimize what we have to pay for. I mean, what we pay for is typically electricity to spin a motor, which is spinning the compressor. That's your work input term here. So we certainly want to minimize the denominator, maximize the numerator, and that's the nature of coefficient of performance. I mean, just like it was for the thermal efficiency, right? This is a performance parameter. We want it to be as big as possible. So here's a performance parameter for refrigerators, freezers, air conditioners. However, there's another type of device that's called a heat pump. Honestly, we don't use heat pumps that much here on this part of the United States. We have lots of natural gas. It's cheap. It's already in pipelines. It goes right into your house. And it's actually cheaper typically to heat up a home using natural gas that's burning than to use a refrigeration cycle where the heat that's rejected is just rejected into the house. Nonetheless, a heat pump is a refrigeration cycle, but what you're effectively doing is taking heat out of the cold outside air. You're essentially refrigerating it, keeping it even colder, and then the heat that gets dumped out of the cycle at higher temperature is the heat that gets dumped into your house. So some of you may have a single air conditioner / refrigeration unit that's in your apartment or your house. It also is going to operate as a heat pump in the wintertime, right? Air conditioner in the summer, heat pump in the winter. All you really have to do is change the location of a few valves, and you just basically get the thing to dump the heat out into your house instead of dumping the heat out like you do in the summertime out of the house. Nonetheless, for a heat pump, it's clearly QH, which is our desired heat transfer. So the coefficient of performance, and we use the subscript HP just to make the distinction between that of a refrigerator, freezer, air conditioner. This is just going to be the rate of heat rejection at high temperature divided by the net power input, or again on a per unit mass basis. We can just write it as lowercase QH over work net. And again, this term or this equation can also be ever so slightly modified, and we will get 1 over 1 minus, and then this will be QL over QH. Or again, I'll write it as a rate Q dot L over Q dot H, or if you will, 1 over 1 minus lowercase QL over QH. Okay? So this is the equation you would use then for a heat pump. It's still a refrigeration cycle. There's no difference really in the way that we analyze the cycle, whether it's a heat pump or a refrigerator, freezer, or air conditioner. We just simply use a different equation because we have a different desired heat transfer. So any questions on any of this? All right, great. Let me also just make a note here, and I believe I mentioned this last time. In all these various equations associated with cycles, whether it's efficiency or coefficient of performance, all the terms that we're using are absolute values or magnitudes, if you will, okay? You could see that the minus sign in here includes the rate, or I should say, not the rate, includes the direction of the heat transfer. This is heat input. We subtract from it the heat output, okay? So Q dot L is a positive term. It's a magnitude. Q dot H, of course, is a positive term. So the minus sign appears within the equation. Same thing here with the coefficient of performance for these various refrigeration cycles. All the terms are magnitudes. You know, it's the magnitude of the heat input. It's the magnitude of the heat rejection. Anyway, so just as a reminder, and of course this was hopefully made clear to you previously in your first course in thermodynamics. So this actually then ends the review, and we're about to begin new material. So any questions on anything we've talked about these last couple of days? Anything confusing to you? All right. So now we begin gas power cycles. Now, in ME301, you should have covered the Brayton cycle, at least the simple ideal Brayton cycle, maybe even simple non-ideal Brayton cycle, which is a gas power cycle. But that's not the one we're going to start with. We're here in chapter, 9 now, I guess. And in chapter 9, I just want to go through the material in the same order that the author's gone through it in the textbook. So we're actually not going to start with the Brayton cycle. We're actually going to begin with the Otto and the diesel cycles. But before I even get into that, let's just in general talk about gas power cycles so that we understand what is the nature of a gas power cycle. So the first thing that should be noted is that we're talking about heat engines. Okay. These are heat engine cycles. Heat input, work output, it's a heat engine cycle. I also want to note that for this particular category here in chapter 9, we're specifically talking about a gas being the fluid that's moving through the cycle. The gas is doing the work. The gas is having required work put to it. So this gas power cycle basically has a vapor as the working fluid. Okay. There's no phase change. We're not talking about steam cycles where water would ultimately boil into steam, which could be used in a steam turbine. We'll get to that, but not yet. That's going to be a little bit later. But for now, it's a vapor that's the working fluid. And also in this class, we're going to make a variety of assumptions to make our life easier. Certainly these assumptions will cost us a little bit with regards to accuracy. But as this is really your first introduction to these types of cycles, it's hardly worth it to use complicated cycles. So let's keep things kind of simple. And here are the various assumptions that we're going to make here. First of all, there's no friction in the connecting pipes. Okay. So for instance, let's say, well, in fact, even the word connecting pipes is a little bit misleading. But I'll put it this way anyway. So let's assume we were talking about a Brayton cycle just for illustration. We know that we're going to have compression in a compressor, and then the gas is going to travel some distance, and then we'll have heat input in the combustion chamber, and then the gas will travel some distance, and then we have work output in the turbine. We're assuming there's no friction in these connecting pipes, that is, in between the individual devices. Okay, so maybe I should really write it that way. I'll just leave it like this. So there's no friction. And what this really tells me is that the thermodynamic state leaving one device is exactly the same as the thermodynamic state entering the next device. Okay, we're not losing anything. So that's what this really means. So the state leaving one device equals the state entering the next device. Okay. And if you want, you could even use the word process as opposed to device. Perhaps that would be another way to think about it. You know, we have a heat transfer process. We leave that process. We go into a work process. We leave that process, go into a heat transfer process. So the state's the same as we leave one and then enter the other. Okay? Let's also note that everything is well insulated. In other words, no heat losses. Okay, so we know that in the real world, things are not always well insulated, and we may have heat losses into the surrounding. The turbine might have heat rejected from it, just lost to the surroundings, the compressor, et cetera, et cetera. We'll assume that everything is insulated very well, and therefore there's going to be no heat losses. Okay, another thing we might note here is that we're just going to assume that air is the working fluid. Okay. So not only are we ignoring any kind of phase changes, which of course there won't be for these cycles anyway, as we talked about above, that is, it's always a vapor. Here we'll note that that vapor is always going to be air. Okay. So this is typically just called an air standard cycle. Okay. So we're only going to be dealing with air standard cycles. I might note that even though this does, again, well, I guess I said this before, this does cost us some accuracy, but this is really the best way to learn the material. Let me also note that as we're dealing with air, sometimes we're going to assume that air acts as an ideal gas with constant specific heat. Sometimes we'll assume that the air is an ideal gas with variable specific heat. But any way we look at it, not only is air going to be the working fluid, but also air is going to be treated as an ideal gas. Okay, so this also simplifies things quite a bit, but it does help us learn the material. Okay. Another thing we would note is that the air moves in a closed loop. Sometimes we just call this a closed cycle. Okay. Now, is that really happening in the real world? No. I mean, in a real gas turbine engine, we don't have anything moving really in a loop, right? We take fresh air in, we compress it, we burn it, we let those high temperature combustion gases, which of course we're treating as air, do work, and then we exhaust right out into the environment and we start with some fresh air all over again. That's not what we're going to assume in this class, just like you didn't assume this in your ME 301 class. And this is not only going to apply to the Brayton cycle, which is the cycle obviously for the gas turbine, but it's also going to apply to the cycles we're going to analyze for internal combustion engines. In fact, that's really the first thing that we're going to cover. We're going to start talking about that today. Now, even in an internal combustion engine, it's not really a closed cycle, is it? We take fresh air in through the intake valves of the engine. We compress it by the action of the piston. We burn it as the spark plug ignites the mixture. Work is done. And then we open the exhaust valve and we expel the exhaust gases. That's what's really happening, but not in this class, okay? Not in your first class in thermo, at least your first class dealing with cycles. Air moves in a closed loop. There's no exhaust process. There's no intake process. Okay, it's just air moving in this closed loop. Okay, and furthermore, we would like to note that there's no real combustion. Okay, what we do is we basically just assume that there is heat exchange equal to the amount of heat that would otherwise be generated by the combustion process. So there's no combustion, just heat exchange. Okay. So these are just some of the things we need to understand with regards to the relatively simple gas cycles that we're going to deal with. These are all air standard cycles, and again, this is going to greatly simplify things. Once again, we could either assume constant specific heats. If we assume constant specific heats with the specific heats taken at room temperature, we might often call that the cold air standard assumption. Or we could use variable specific heats. And of course, with variable specific heats, we use the data that's in table A17. And again, we just started looking at this last Wednesday. Okay. Now, what is the performance parameter of interest? Well, obviously, It's a heat engine cycle, so it's a thermodynamic efficiency, or again, thermal efficiency that we're going to be calculating as we go through these different gas power cycles. And there are many different cycles that we're going to get into. So let me just pause then. Any questions? Let me just remind you of one other thing. There is a cycle that's called the Carnot cycle, right? This is an ideal cycle that we cannot achieve, right? It involves processes that are ideal processes, isentropic processes that we as mere humans are not capable of producing. Sometimes we look at the Carnot cycle anyway because it does give us a limit, right? Nothing can have an efficiency higher than that of the Carnot cycle operating between the same temperature limits. Nothing can have a higher coefficient of performance than a Carnot cycle operating between the same temperature limits. We're typically not going to deal with the Carnot cycle in this class, but you will see some words about it as you go through this section of the book. For the most part, we're just going to ignore that. We're interested in the actual performance of a real heat engine operating on the gas power cycle, not some idealized cycle operating between the same temperature limits. So sure, read about Carnot cycles, but don't worry about it. You're not going to be required to solve any problems dealing with that. Plus, you already learned about the Carnot cycle last quarter, so there's no need for us to really get into it in this quarter. All right, so now we begin the, let's say, initial discussion of the first type of cycles, and this deals with reciprocating engines. Okay. So when we talk about reciprocating engines, we're talking about vehicle engines, automobile engines, truck engines. And in all of these situations, what we have is nothing more than your good old friend, the piston cylinder device. You studied these quite a bit in your Thermodynamics class, ME 301. And now what we might realize is that we can actually operate a heat engine cycle based solely on a piston cylinder device. So what we would have is the cylinder with a piston in it. The piston is going to move back and forth. The piston is going to move a certain distance as it goes from the top to the bottom. So I'm just going to show the same piston with some dashed lines to represent the highest position and the lowest position. Right here at the very top, we call this top dead center, or just TDC for short. Some books just simply call it top center. And then at the bottom of its travels, the piston is at bottom dead center, or bottom center. And we just abbreviate that, BDC. Okay? So the piston is moving back and forth between top center and bottom center. Keep in mind that there are certain volumes within the cylinder associated with these two positions, right? When the piston is at top center, the volume is actually the minimum volume, and that would be the volume within the cylinder. By the way, you're never going to have the piston go all the way up and hit the very top of the cylinder wall. In a real engine, I mean, you can't do that. There's spark plugs up there. The valves are opening into that space. There's instruments in the engine that would certainly be damaged if the piston went all the way to the top. So it doesn't. There's always going to be a certain minimum amount of volume. In fact, it's really called the clearance volume. So if you ever read the words clearance volume, that represents the minimum volume associated with the cylinder in the engine. Okay, at bottom center, this is the maximum volume. And there's no specific name for the volume at bottom center. Although there is one other term we should be aware of. It's called displacement volume. Sometimes we just use VD, D for displacement. This is simply the difference in volume between the maximum position and the minimum position. Okay? So this is just really V max, which is the volume at bottom center, minus V min, the volume at top center. And I should note too that this is the volume that you see printed on the side of all the engines you would buy. Well, the cars you look at has an engine like a 1.5 liter engine. That's the displacement volume that they're presenting, right? It's not the clearance volume. It's not the total volume at the maximum position, that is at bottom dead center. It's actually the difference between the two. Okay, so this is just another term that you should be aware of. Now, keep in mind again, we're specifically dealing with closed cycles here. We assume that there's just air in that cylinder. The air is being compressed and decompressed continually over and over and over again as the piston moves up and down and we go through a particular cycle. Again, with the understanding that it's just air, there's no intake and exhaust processes, there's no real combustion. We're just transferring heat to the air, we're letting the air do some work. So this is clearly an air standard cycle that we're analyzing. Let me also note that the distance traveled as the piston moves from top center to bottom center is called the stroke. So again, the stroke is a distance that the piston moves as it moves from top dead center to bottom dead center. Okay? And then also note another term of interest is what we call the bore. The bore is simply the cylinder diameter. So often you would be given data for the stroke and for the bore, and since the cylinder is just a right circular cylinder, it's pretty easy to use that data, the bore, in order to find the volume, right? Just pi over 4 times the diameter squared, that gives you the area, and times the length will be a volume. So the bore is nothing more than the cylinder diameter. So again, these are some of the terms that you should be aware of. Another thing you should be aware of as we begin talking about this material is what's called the compression ratio. So the compression ratio is R. Please note that the compression ratio is a volume ratio, not a pressure ratio. As you've covered the Brayton cycle in your previous thermal class, you often had to deal with the pressure ratio. This is not a pressure ratio. This is simply defined as the maximum volume divided by the minimum volume. In other words, it's going to be the volume at bottom center divided by the volume at top center. So it's really no more complicated than that. But that is something that we're going to have to deal with. It is one of those terms that will be important as we try to analyze our cycles. Okay, so that's the compression ratio. Another term that we need to talk about is what we call the mean effective pressure. Now, the mean effective pressure is not a real pressure. It's not a pressure that is actually seen in an engine. It's really just a pressure that's used for comparative analysis as we compare different engines. What we would do is we say, well, if the net work that's done by this engine is done at constant pressure, that pressure is called the mean effective pressure. So the mean effective pressure or we would just abbreviate it MEP, is the, let's call it the assumed constant pressure that would exist if the network were done at constant pressure. As the piston moves through the displacement volume. I guess I wrote constant pressure twice. Sorry, I'm a little bit redundant today. Okay, so at constant pressure, as the piston moves from, well, bottom center to top center, or vice versa. Okay, now we should know how to figure that out. So we have a certain network output, and if this was done at constant pressure, that pressure being what we now call the mean effective pressure, well, the work term for a constant pressure process for a closed system is just the pressure times a change in volume, right? So that's just going to be the volume at its maximum position, which is bottom dead center, minus the volume at its minimum position, which is top dead center, right? So V max minus V min, okay? In other words, this assumed average pressure, this performance parameter called the MEP, is really just the net work output divided by Vmax minus Vmin. Or we can even just write this as the net work output divided by, well, the displacement volume, right? The displacement volume, Vd, is exactly that difference between the maximum and the minimum volume. So this, again, this is a performance parameter that we will often use to compare different engines, but it's not like we always use it. Engines can operate at so many different speeds. They can operate at so many different fuel-to-air ratios with so much energy being produced. They can operate at so many average pressures, high pressure, low pressure. Often we use the MEP just as a way of comparing different engines. Lastly, I might note that if we just divide by mass, both numerator and denominator, then this is going to be the net work output on a per unit mass basis. And then the displacement volume on a per unit mass basis. So we can just write this as a lowercase v sub d. Or if you will, instead of the displacement volume, this is displacement volume on a per unit mass basis. There's a difference between the specific volume at the maximum minus that at the minimum position. So divided by the specific volume at the max minus the specific volume at the minimum position. And again, recognize that Vmax is the bottom position, right? That's at bottom center, and V minimum is at top center. Okay. So this is just some of the basics that's going to apply to all of our reciprocating engines. And now we should begin looking at different types of engines. Now, there's actually two different reciprocating engines that we're going to deal with depending upon the type of fuel that we use. Okay, one type of engine is called a spark ignition engine, which we just know of as a gasoline engine. And the other type of engine is what we call a compression ignition engine, which is what we just know of as a diesel engine. Okay, so those are the two basic engine types that we're going to deal with. And they actually operate just a little bit differently. The gasoline engine can be called the spark ignition engine, and it actually requires a spark plug in order to ignite the fuel-air mixture. A diesel engine doesn't require a spark plug. Just simply going through the compression process of the air as the piston moves from bottom to top center achieves a high enough air temperature, and when the diesel fuel is injected into that air, it immediately begins to combust. Well, maybe I shouldn't say immediately. It takes a fraction of a millisecond, but it starts to combust essentially right away. And we call this a compression ignition engine. Okay. And in fact, as we analyze the actual combustion process and analyze the way in which the heat transfer takes place during that heat input process, we realize that the two are just a little bit different here as well. If you have an air-fuel mixture, which is actually in a real engine going to be compressed as the piston moves from bottom to top, as soon as the spark ignites, the combustion process begins immediately, and the whole thing takes place more or less when the piston is at top center. So this is approximately constant volume combustion. Now, maybe I won't even write the word combustion. We know there's no real combustion in this class. I mean, there is combustion in the real world. In this class, it's just heat input. So here we're going to have constant volume heat input representing our combustion process. And for the diesel engine, what we find is that the fuel injection process takes a finite amount of time. Yes, you'll begin fuel injection as the piston hits top center, but it's a fuel injection system. It takes a finite amount of time. The piston actually starts moving immediately upon the combustion process taking place. And what we find is that in this type of engine, we have approximately constant pressure heat input. Now, because of that, we're going to have to analyze these two different types of engines using two different types of cycles. And of course, we'll get to those two cycles here in just a couple of minutes. Now, there are certainly similarities between the two. So before I just break these two apart and start looking at each one individually, let's just look at the things that are similar. So certainly in both of those cases, there's going to be 4 processes of interest. Okay. So what are these 4 processes? Well, first of all, there's going to be a work input process. Okay. In other words, we're going to have air. If it's a diesel engine, air-fuel mixture. If it's a gasoline engine, again, don't worry about that. We're assuming it's just air for our analysis. But still, the first process is work input. Basically, this is where air is compressed as we move from bottom to top center. I'm teaching an engines class this quarter, and there we just use the words bottom center and top center. Here, I got to remember the D in between. So bottom dead center to top dead center. Okay, so this is the first process that we're going to deal with. It's just going to be a work input process. After the work input takes place, then that's when either the combustion process begins under the influence of the spark plug, or the combustion process begins as fuel injection occurs in the diesel engine. So that's our second one. So this is heat input. Okay. Now the heat input is always going to begin at top dead center. And of course, if it's a gasoline engine, it's going to end at top center too, right? The volume's going to be constant. On the other hand, if it's a diesel engine, the combustion process is going to take a finite amount of time. The piston is going to move. So I'm going to say heat input, and I'll just note it begins at top dead center, with the understanding, of course, that it's not going to stay at top dead center for the diesel engine, but certainly will for the gasoline engine. Again, we'll break these out separately, and I'll summarize this again for you. Now, what about the third process? Well, the third process would be work output, right? The air's been compressed, heat's been added to it. We have very high temperature, high pressure gas now inside that piston cylinder device. The cylinder has a high pressure temperature gas. It pushes the piston downwards. So the third process is going to be our work output process. Okay, so this is going to occur as we go from, well, now top dead center to bottom dead center. Okay, and then the fourth process is going to be our heat output, or we can think of it as heat rejection, whichever term you want to use. Please keep in mind that this is going to occur at bottom dead center. Once the piston is moved to the bottom, you open the exhaust valve typically and just let everything flow out. So heat output is going to occur at bottom dead center. It's a constant volume process. Okay. So these are the basic processes that we're going to have to analyze within our heat engine cycle. One other thing I just want to mention briefly, because as I've been describing the engine and the intake and the exhaust process, it turns out there's actually 2 different ways in which we can undergo the intake and the exhaust process. These have absolutely nothing to do with the thermodynamic analysis. Thermodynamic analysis, everything we do, if you will, is only going to be a function of the amount of work in and out and the amount of heat in and out. Okay? But in a real engine, there's definitely an intake and exhaust process. So I do want to cover this very briefly, and certainly it's discussed in your book, but just with the understanding that it really doesn't apply to any of our analysis. Okay? It's just to give you a better understanding for the nature of different engine types. And what I'm about to describe will apply just equally to the spark ignition and the compression ignition engines. In other words, the gas or the diesel engine. And this just has to do with the way the intake and exhaust process takes place. So the intake and exhaust processes could be done 2 ways. Okay? Now, one way is if we have what's called a 2-stroke engine. Okay? And in fact, as I've gone through the basic discussion, it's really more representative of a 2-stroke engine. You go through the process, right? Your air's in the cylinder, you compress it, heat added to it, it does work as it expands, and then you have the heat rejection process, which really we know is done through the exhaust process. I mean, in the real world, we're exhausting whatever combustion gases are left within the cylinder, and we start all over again. But that's what I want to talk about here. In a two-stroke engine, you just simply open the exhaust valve, and the exhaust just shoots out. This all takes place when the piston is essentially at bottom center. So the exhaust comes in, it forces the intake out. There's no separate strokes as the piston moves up and down. It doesn't. In a two-stroke engine, exhaust and intake occur at bottom dead center after the work output is done. Okay. Now, these types of engines are really only used for small applications where weight is important. For instance, a weed whacker, a moped, those would be pretty typical of two-stroke engines. Personal watercraft, although these engines are more polluting, so some lakes don't allow two strokes, like Lake Tahoe doesn't allow two-stroke anymore on the lake because of the pollution, and we're not going to get into why they're more polluting. But nonetheless, they're very common when we have weight as our main concern. On the other hand, we could also have a four-stroke engine, and the vast majority of engines are four-stroke engines. Your car engines, your truck engines, your boat engines, I mean, these are all four-stroke engines. So what happens here is you actually go through two separate strokes of the piston. We still have the thermodynamic cycle, right? As the engine rotates one rotation, we're still going to compress the air, we're still going to add heat to it, it's still going to do work as it moves down the piston or pushes down the piston. But at the end of this process, we're actually going to go through two more physical strokes. The engine is going to rotate one more time, and on that rotation, one stroke will push the piston upwards and force out the exhaust gas while the exhaust valve is open. And then the fourth stroke is where the piston is drawn downwards, and it sucks in the fresh charge of air through the intake valve. And then you start the thermodynamic cycle all over again. Now, that's a much more efficient process, much more efficient at exhausting the combustion gases, much more efficient at drawing in the fresh charge of air. But again, from our standpoint, it doesn't matter. From a thermodynamic standpoint, none of this matters. But again, I want to make sure you understand it. So here, exhaust and intake occur with two added strokes. Basically, bottom dead center to top dead center is the exhaust. And then from top dead center back to bottom dead center, this is going to be our intake. Okay, so just be aware that these processes do occur, and that's how a real engine operates. Okay. One last thing to note on this before I move ahead. The main reason your two strokes are smaller and lighter is because work is being done with every rotation of the engine. On a four-stroke engine, work is only being done with every other rotation, right? In a four-stroke, you have one rotation which goes through the thermal cycle, and then the next rotation, nothing really happens from a thermodynamic point of view. We just have the intake and exhaust processes, right? In a two-stroke engine, not true. You go through one cycle, and you immediately intake and exhaust, or really the other way around, right? You do the exhaust and intake, and then the next engine rotation, you do another thermodynamic cycle. Each engine rotation goes through a complete thermodynamic cycle. So what you can get by with is a two-stroke engine that's essentially half the physical size of the four-stroke, and even if it operates at the same speed, even if it operates with the same displacement volume, it's essentially going to produce twice as much power because it's producing power with every engine rotation rather than power with every other engine rotation. So it's basically an engine half the size for the same amount of power, or if you will, twice the power if it's the same size between a two and a four-stroke. You should be aware of these things. If you're more interested, well, take ME 412. It should be offered every spring quarter. Well, nowadays, spring semester. All right, so any questions just in general about the nature of these reciprocating engines, how they're really just piston cylinder devices, and we're just using air as a closed cycle? Yes? Right. You could have a two or a four-stroke spark ignition, or you could have a two or a four-stroke compression ignition engine, right? Okay. So that now, as introduction, brings us to our first thermodynamic cycle, which is the Otto cycle. Not Otto as an automobile, but Otto as in the German scientist that invented all this about 150 years ago. So Otto cycle. Now, the Otto cycle is an ideal air standard cycle. Please note that this is an ideal cycle. We're not going to be dealing with anything like isentropic efficiencies. We're going to assume that every process is an ideal process, and that's going to be the way we analyze this. Again, it's an air standard cycle like all the cycles that we're going to be analyzing here. The ideal air standard Otto cycle is used to model a gasoline engine, or if you will, the spark ignition engine. Okay. So this particular cycle, well, it has the strokes that we talked about: work input, work output, heat output. But now what I want to do is just go into a little more specifics. So let's look at these processes on some thermodynamic property diagrams. And there's really two property diagrams that we would typically use. One would be a PV diagram, and the other would be our good old TS diagram. Okay. So let's just look at these processes first on the PV diagram. So on the PV diagram, we would note that the cycle begins at what I'll just call state point 1. This is when the piston is at bottom center, and we're just about to begin the compression process, the work input process. So at this point, whatever is within the cylinder is going to be probably close to atmospheric pressure. The volume is going to be at its maximum because it represents bottom dead center. So we're going to be way over here somewhere. So that's state point 1. And in fact, as I go through each of these processes, the first process will be 1 to 2, and this is called compression. So there's certainly going to be some work input. So the compression process takes place. The air is being compressed into a much smaller volume until we get to top dead center. And of course, during the compression process, the pressure is going to rise. So we'll end up with a state point 2 that's over here somewhere. And let's just note the volume at both top and bottom dead center are here and here. Now we undergo the heat transfer process. Oh, by the way, I should not just put compression, I should say work input, and clearly there's work input taking place. Okay. By the way, I'm just using lower cases, W's and Q's and all that. You could use dots, you can use capital letters, it doesn't matter. Okay, now we have the heat input process, right? So this will be state point 2 to state point 3. I mean, in the real world, this is combustion, right? This is where you burn your air-fuel mixture. But for us, this is just heat input. So this is our Q in. And this is done at constant volume, okay? This takes place when the piston is at top dead center. So we have a vertical line as we go from state point 2 to state point 3. So heat input at constant volume. Okay. Now we undergo the next thermodynamic process. This would be from 3 to 4. And this is typically called the power stroke, or this is where power is actually developed. So here the piston, under the influence of the high temperature air, again, combustion gases in the real world, we now push the piston down. Of course, as we do so, we're creating work, and the thermodynamic state's going to drop, and we end up with state point 4 here. The pressure is going to drop, the temperature is going to drop, the internal energy is going to drop. So this is our work output term. Oh, it looks like I forgot my Q in, so don't forget to put that. Q in over here from 2 to 3. Okay. Anyway, then at state point 4, this is where we have the heat output or heat rejection. So from 4 to 1, heat rejection. And again, this is done at constant volume. So we just go vertically down from 4 to 1, All right, so heat rejection at constant volume. Okay. By the way, I guess up here I could have put work out next to the power term. Heat rejection at constant volume. We'll just call this Q out. So these are the four processes that are taking place. Now again, don't worry about the intake and the exhaust processes. Again, that was just for your understanding, and it really has nothing to do with our analysis. All right, so a couple of other things to note here, and this will be more evident as I go through the TS diagram. Remember I had mentioned that this is an ideal cycle. So what happens to the entropy as we go through the initial compression process from 1 to 2? Well, it's ideal, right? The work is done, but we're assuming that there's no heat transfer. We're assuming that it's a reversible process. It's a very ideal process. So the entropy is going to be constant. So state point 1, well, this is going to represent the lowest possible temperature in the cycle. So state point 1 is over here. When we go through the work input process, it's actually isentropic. So the temperature is going to rise as we are compressing the air, but the entropy is going to remain constant. Okay? So this is our work input. And perhaps over here, we would note that this is an isentropic process. Right? Isentropic meaning constant entropy. Now we have the heat input process. With heat input, the temperature is going to rise, the entropy is going to rise, and we're going to end up with a state point 3 up here somewhere. Now we're going to go through the work output process. And again, in an ideal cycle, we're assuming that work is done adiabatically and reversibly, right? That's what ideal means in the context of these cycles. So the work output is another isentropic process, just like work input. And we're going to end up at state point 4, again, at the end of a vertical line from 3 to 4. So over here, you might also want to note that this process is isentropic as we go from 3 to 4. And then last but not least, we go through the heat rejection process. Let me show my other Qs. It works. So Q in from 2 to 3, work out from 3 to 4, isentropic. And then from 4 to 1, we have our heat rejection or the heat output. And again, this is done in constant volume. So we know based on our cycle analysis that we have two constant volume processes, right? We call these isochoric if you prefer. And then we have two constant entropy processes, isentropic. And we're going to have to use those in order to go through the analysis of any one particular engine. Okay. So what I'd like to do next then is just go back to the thermodynamic efficiency equation and make sure that we understand how to analyze it for this particular type of engine. Again, these are closed cycles. We have a constant mass of air that's simply continuing to move through different processes within the cycle, but these are closed systems, right? So the first law, as we utilize it, is certainly going to be for a closed system. All right, so what would my equation be now for the thermodynamic efficiency? So let's find the thermodynamic efficiency. Again, this is a heat engine, so it is a thermal efficiency, not coefficient of performance that we're dealing with here. We would again note that as we are analyzing these processes, they're ideal. We're using constant specific heats. Again, I want to emphasize that we're going to neglect any kinetic and potential energy associated with any of these processes. So what would the equation be then for the thermodynamic efficiency? Now, I gave you various forms of it earlier today, right? I mean, the net work divided by the heat input is the basic form of this equation. Again, we might write it as 1 minus the heat output minus the heat input. I think I'm going to start using out and in rather than H and L. I mean, high would be high temperature heat input, H for high. So I could have that in the denominator. I could have QL, for low temperature heat rejection, but I think it might be a little more clear if I just use in and out at this point. So this is going to be another version of the equation. I can write it as total Q out over total Q in. I mean, there's just different forms of the same equation. Now, in this particular case, I have 4 individual processes, 2 of which, of course, are going to have to be included in that thermal efficiency equation. We have a closed system. There's no appreciable kinetic or potential energy change. We know that for heat transfer processes, they're done at constant volume, right? So there's no work, right? For a constant volume process, no work, no boundary work, so there's no work. So with all this in mind, we can now just substitute in the appropriate version of the first law. Now, let's just look at this term, using the lower cases. How much heat is going to be rejected? Well, from the first law, that's just the difference in the internal energies, right? We know that the equation says heat transfer minus work equals change in internal energy plus change in potential and kinetic energy, but there is no kinetic or potential energy change, and there's no work during these processes of heat transfer because it's constant volume, so we simply get the difference of internal energy between point 4 and point 1. So U4 minus U1 is in the numerator, and then in the denominator is the heat input as we go from 2 to 3. Again, with no kinetic or potential energy and no work, we just have an internal energy change from our first law. So that's just going to be U3 minus U2. Okay. So again, this is just from the first law for a closed system. And again, assuming that there's no kinetic or potential energy changes and noting that there's no work. So hopefully everybody can see that. All right, so now what do we want to do with these particular equations? Well, at this point, we have to, decide whether we're looking at a problem with ideal gas with constant specific heats or variable specific heats. Certainly, if we use variable specific heats, we're just going to use the internal energy data that appears in our textbook in Appendix A17, so I don't need to change that equation at all, right? But on the other hand, if I assume constant specific heats, then we know that an internal energy change is just equal to CV times a temperature change, so I definitely need to make some modifications to that particular equation. Before I do it, one last thing to note. We are at times going to be interested in finding the net work. Maybe I'm not going to need it immediately, but we certainly know that the net work is just work out minus work in. And again, from the first law of thermodynamics, we're assuming these are ideal processes. The work is done without any heat loss. And if we assume no appreciable kinetic or potential energy change, well, the work terms are also just equal to internal energy changes. So the work out, that's going to be between 3 and 4. So just U3 minus U4. And then the work in is going to be that between point 1 and 2. So U2 minus U1. And that's how we would find the work for these particular processes. Now, again, if we have ideal gas with variable specific heats, we're just taking internal energy data out of our tables, and we don't have to modify these equations at all. If we're using constant specific heats, we have to make a slight change. So let's just briefly look at that. So if we have constant specific heats, then we would just note that an internal energy change is equal to CV times a temperature change, right? So we can go all the way back to these various equations. We would be able to show that the thermal efficiency then is just 1 minus, and then in the numerator, we're just going to have a CV times T4 minus T1. In the denominator, we'll have a CV times T3 minus T2. You can see that the CVs cancel. And we'll find here that the thermodynamic efficiency is only going to be a function of temperature. Okay? Now, I can actually modify that equation a little bit further, and I'll get to that in just a moment. But also, I just wanted to write out the net work equation. Right? Again, we're specifically looking at constant specific heats here. So the internal energy change becomes CV times the temperature change. And we just get CV and then times T3 minus T4 and then minus T2 minus T1. I've just factored the CV entirely out and moved it over to the far left-hand side of the right-hand side of the equation. Okay. So this is something we would note. Now, I can go back to the efficiency. One thing I'd like to show is that we can calculate the efficiency based only on the compression ratio. Now, unfortunately, I've just run out of time, so We'll continue this on Wednesday. Certainly you're not at a point where you can start doing your homework problems. I mean, some of you could certainly start if you want to read ahead a little bit, but we're really not quite there yet. So we'll continue this next time, talk about Otto Cycle, go through some example problems, move on to the diesel cycle. Anyway, see you then. Reminder, don't forget to show proof of prerequisites. If you have it today, you can bring it up now, or just bring it up anytime within the next week or week and a half, really. So, see you all Wednesday.